Yeah, so good morning, good evening, and good afternoon, everyone, depending on where you are in the world. We're very excited about this webinar with Dr. Chris Clarkson. Obviously, I'm not Chris, but I'll do the quick introduction here of the webinar today and go through a few logistics and then introduce Chris and also facilitate the Q&A after the presentation. Just before we get started, a few meeting logistics. We have around 100 registered participants. The meeting is on what's called WebEx events, so everybody is muted by default. But if you have any questions, feel free to ask them in the Q&A chat box that you can find down to the right. So just to emphasize, there's a Q&A chat box, and it's also a way to do just a chat. So try to do the Q&A in the Q&A section of the system. Because then it's easier to keep track of. The presentation is scheduled to be around 45 to 60 minutes, and there will be questions after that that will be answered. And the meeting is also recorded. The recording will be available on Whitson Academy, which is our online learning platform. So example courses can be items related to what we do at Whitson, but also these topical webinars on different topics as this on RTA. For those that have been joining a lot of our courses in the past, we have all our public courses. They can be found on whitson.com/training. That goes for both for kind of theoretical courses and also software-related courses in softwares that we offer here at Whitson, for instance, Whitson Plus. So with that short introduction, I would like to introduce the speaker, Dr. Chris Clarkson. A very nice picture of my friend here. He's a professor at the University of Calgary. I know a lot of the people that's joining this call know very well who Chris is, and he has a very, very respectable and actually a very involved path in a lot of different items in the past. But he's in terms of degrees, PhD from University of British Columbia. At least the things that I really enjoy is that he's been a SP Distinguished Lecturer in the past around 2009, 2010, and he had, in addition to that, he had numerous other technical awards as well. He has also had 11 years of experience in the industry, working for Burlington Resources and ConocoPhillips before he now, joined as a professor at University of Calgary since around 2009. Most importantly for me, though, is that Dr. Chris Clarkson is a very good guy, and you'll see that throughout this presentation as well. So with that, Chris, I'll stop sharing, and then I'll make the floor yours by making you a presenter, and then from there, I'll stay muted.
Great. Thank you so much, Matthias. Welcome, everybody, and thanks for attending today. Just going to go ahead and share my presentation with you and start up my laser pointer, all that stuff I need to do here. All right. So again, welcome, everybody. Really great to be able to present this to you today. So on behalf of my co-authors, I'd like to present a revolutionary new core analysis method for unconventional reservoirs based on rate transient analysis theory. We call this technique RTAPK. And if you're interested in learning more about the subject, there's some references here at the bottom. I also provide them at the end of the presentation in case you're curious about some of the things I talk about. So as you'll see, this was really an attempt to merge the concepts of core analysis with rate transient analysis. So core analysis obviously is what we do in the laboratory, but RTA is traditionally applied to production data in the field. So the question is, how do we kind of link these two things together? And this is really our attempt to do that. So I'll begin with a brief outline, first provide a little bit of background. Necessarily, I'll start with a little bit of information on rate transient analysis. Probably a lot of you are familiar with it already, but just to give you a little background on that, and that'll lead us to our problem statement, which is really around, as I suggested previously, how do we make core analysis more consistent with production analysis in the field. In other words, how do we design experiments and analyze data to be more consistent with how we do this in the field with real production data? So I'll then move on to our solution. We first came up with the idea of doing this type of an analysis on core back over 10 years ago, and we pursued the topic theoretically. We used simulation, and we'll talk about that briefly. But more importantly, and more recently, we've been able to demonstrate that we can do this in the laboratory. And so we'll show you an example of what I call a proof of concept study, which gave us some confidence that this could work. And then in the past 2 or 3 years or so, we've been trying to further develop the method, expand its capability, and use it really to start addressing some fundamental problems that we're facing in rate transient analysis, some questions that we simply cannot answer using field data because we can't take the reservoir to the surface and analyze it directly. So we can take little pieces of it though. And so we'll talk a little bit about what we're currently working on and some future work. And then I'll wrap it up with some conclusions right at the end of the presentation, then allow for some Q&A to answer some of your questions about the method. All right, just a little bit of background. We know that multi-fractured horizontal wells are currently used to develop and exploit low permeability, or what we call unconventional reservoirs. And here I'm just showing a very simple, maybe somewhat dated conceptual model of a multi-fractured horizontal well completed in a tight or shale formation where we have these multiple hydraulic fractures that can have a complex geometry that's been developed along the length of the horizontal well. And we know that a combination of reservoir permeability and fractures control the production. So between the fractures and the unstimulated reservoir, we need to characterize reservoir permeability that delivers our fluids to the fracture system. So we know that both the reservoir permeability and fractures ultimately control the performance of these wells, whether we're producing oil and gas out of them or injecting CO2 into them. We still have to make this characterization to understand well performance. So we know that rate transient analysis is a common method that's used to extract reservoir and fracture information from well production data or using field data, and specifically using flow rates and flowing pressures. And one of the first things that we need to understand with these systems, particularly multi-fractured horizontal wells, is what to expect in terms of the sequence of flow regimes, or those characteristic flow patterns to a well over time. And this is a simple conceptualization of flow regime sequence for a multi-fractured horizontal well. It was first proposed by Song and Economides back over 10 years ago now. And it makes quite a few assumptions about our well here. It seems we have planar bi-wing fractures that are equally spaced along a horizontal well, and we know that that's an idealistic representation. But nonetheless, it's kind of a useful starting point to show that there can be a progression of flow regimes over time with these wells. So for example, at early time, we may see linear flow of our oil and gas to our hydraulic fractures, and we identify this on our log-log diagnostic plot as a half slope on our derivative plot. This first linear flow regime we call interfracture formation transient linear flow, and after the pressure transients have communicated between the hydraulic fractures, we may enter a period of what we call interfracture boundary flow or pseudo-boundary flow. We can identify that as a derivative of either 1 or less than 1, depending on whether there's inflow from outside the interfracture area. So we see this possible sequence of linear boundary flow, and it's possible to see this again later in the life of the well. So for example, after interfracture interference, we may see linear flow to the horizontal well. We refer to this as interwell formation transient linear flow. And after that, it is possible to see boundary flow develop between offset horizontal wells. And so again, it's possible to see more than one sequence of linear to boundary flow. Now, as I said, this is an idealized sequence. It assumes a lot of things, planar fractures, equally spaced, etc. The real world, we may have unequally spaced fractures. We may have fracture complexity that kind of muddies this this idealistic pattern, but nonetheless an important starting point for understanding flow regime sequences and multi-fractured horizontal wells. Now, if we do recognize linear flow followed by boundary flow, kind of the classic way to analyze at least the linear flow portion of it is to use what we call a square root of time plot. And this image is courtesy of Dr. Dilhan Ilk. And what it is it's a plot of rate normalized pressure versus square root of time. At early time, we may see this straight line behavior develop. We can fit a straight line to the data. And from that fit, we can extract what we call the linear flow parameter, which is the product of the total fracture half length and the square root of permeability, or in some cases, people pose that in terms of total fracture area, square root of permeability. So again, we call that the linear flow parameter. Now, after that period of transient linear flow, we may see a deviation upward on our square root of time plot, which could correspond to boundary dominated flow between the fractures. And if we see boundary flow, we can actually use that information, of course, to extract the fluid in place between the fractures, etc. So kind of classic analysis method of multi-fractured horizontal wells. And again, some complications could be your fracture geometry, multi-phase flow, etc., etc. But this is, again, for a single phase system, this is kind of the tried and true way of analyzing the data. Now, the basic RTA workflow therefore involves flow regime identification, followed by application of models to the flow regimes to obtain our hydraulic fracture and reservoir properties. So I'll show you a simple example. This is some production data from a multi-fractured horizontal well completed in the Cardium play here in Western Canada. It's a tight oil play in Western Canada. And what we're showing you here is semi-log plot of oil in green and gas in red. See the GOR is relatively constant here. And in this particular case, we're assuming that we're more or less producing single phase flow above the bubble point pressure for this particular well. Kind of simplifies things, but we want to keep it simple here at first. And so the steps for analysis are to first identify the flow regimes. So here what we're showing you is a log plot of the oil rate normalized pressure. Actually, it's the integral of rate normalized pressure and the integral of the rate normalized pressure derivative. We use the integral simply because the data can be quite noisy. And on this plot, the green is the integral of rate normalized pressure, and that's the light green, sorry, the dark green is the derivative. And you can see here we have a positive half slope that's developed, which is characteristic of linear flow to the well, followed by a unit slope, which is characteristic of boundary dominated flow. So consistent with that conceptual model we provided a couple of slides back, we're seeing this linear to boundary flow signature. So having identified the flow regimes, we can now systematically analyze those individual flow regimes for properties of interest. So for example, this middle plot here is a square root of time plot for oil rate normalized pressure versus square root of time. You see this early time straight line behavior, and the slope of that will allow us to extract the linear flow parameter. After this green line, which depicts the end of linear flow, we see boundary flow, and we can analyze that boundary flow data using a flowing material balance plot. The flowing material balance plot can be used to extract our fluid in place, in this case, oil in place. So again, a very classic workflow. This is quite a simple example because we're dealing with essentially single phase oil, but this is the workflow that's been historically applied for analyzing multi-fractured horizontal wells. So that leads us to our problem statement. And that is, we know that laboratory data is needed to provide key input for RTA models, things such as porosity, fluid saturation, stress-dependent properties, et cetera, et cetera. However, the experimental boundary conditions of conventional laboratory testing methods, such as those that are used to get permeability, do not match the conditions in the field. So the kind of the classic techniques like the pressure pulse decay, some of the crush rock pressure decay methods that are used, we're not reproducing the boundary conditions that we see in the field, like the well production that we just showed you. Also, in conventional testing, if we're dealing with tight rock, the test times can be quite extensive. Very importantly, unlike the cases that we showed you here with the field data, the flow regimes in the field are not reproduced in the lab. And further, the data is not analyzed the same way that we analyze field data. So that begs the question, why can't experiments be designed to match field conditions and have the data analyzed exactly the same way? And that would provide some consistency between what we do in the laboratory and how we analyze data in the field. So this presentation is really designed to address this particular question. Now, the solution that we came up with quite a few years ago now, over 10 years ago, by myself and some of my students, was to basically analyze core data using RTA and rate transient analysis and pressure transient analysis techniques. And to demonstrate that this could be done theoretically, we went back to numerical simulation, and what we did was we simulated a core plug. So our core plug was our reservoir. Yeah, obviously a very small reservoir, 2 inches long by 1 inch in width. And what we did was we completed a pseudo well in one end of our cylindrical core plug reservoir. We injected gas into the pseudo well. We allowed the pressure to stabilize, and then we produced the gas back out again. And then with known rates and pressures, like we commonly try to measure in the field, we showed that we could analyze the rate and pressure data just like we did the field data. So using rate transient analysis techniques, following the same workflow that we just showed you. Now, this is something that we demonstrated theoretically all these years ago, and more recently we've been trying to show that we can do it experimentally. Now, for this particular conceptual model, in terms of flow regimes, what we expect to see is first transient linear flow of our gas through the core plug. The pressure transient corresponds, or the propagation of the pressure transient, I should say, corresponds to our distance of investigation. That'll come into play a little bit later. And eventually that distance of investigation reaches the boundary of the core plug, and we enter the period of boundary dominated flow. So consistent with the field cases, our field case that we showed you earlier, we see this linear flow followed by boundary flow, theoretically. Okay. So as I said, we demonstrated this theoretically, but it wasn't until recently that we're able to demonstrate that we could do this experimentally. So I'm going to walk you through what we were able to find there. So again, more recently, we've designed an experimental apparatus that allows us to recreate these field conditions and analyze the data in the same way. And so just to show you the results of our proof of concept study that we'll get into a little bit later, here what we're doing is we're showing you a flow regime identification plot for our proof of concept study, where we've taken our gas rate and pressure data and used it to identify flow regimes. So this is gas rate normalized pseudo pressure and its derivative. The derivative is the dark red or brown line here. And you can see a positive half slope corresponding to linear flow and a positive unit slope corresponding to boundary flow, just like we showed you with the field case. And then once we've identified the flow regimes, we can now systematically analyze them using our RTA models for parameter extraction. So our square root of time plot to derive the linear flow parameter, and our flowing material balance plot to derive the fluid in place. The combination of these plots allows us to extract the petrophysical properties of interest, and I'll get into the details of that here in just a minute. So if we compare this with the field example, we see that we're analyzing the data the exact same way, and we're actually seeing flow regimes that are consistent with what we see in field data. So as I said, it was an important proof of concept for us, and over the next few slides, we'll get into some of the details behind what you're seeing in these plots here. So moving on to the proof of concept study, I first want to talk briefly about the experimental setup and procedure that we're using. The experimental setup is very, very simple. Anybody can set this up in their garage if they want. There's a bit of specialized equipment involved, but it's relatively easy put together. So we first start with a biaxial core holder. So that's important because the biaxial cell allows us to apply radial and axial load to our sample so we can reproduce the in situ stress conditions. So that's an important component. And basically how it works is we dose gas from our gas cylinder containing methane, nitrogen, CO2, whatever gas you want to use, inject it into the core holder, shut the valves and allow the pressure to stabilize in the core holder. And then we simply produce the gas out one end through a back pressure regulator. We measure the flowing pressures with a pressure transducer, and we measure the gas rates with a flow meter. So the flow meter and the pressure transducer allows us to gather the rates and pressures for our analysis. So in terms of the total procedure that's illustrated on this slide, so again, we start with an injection, shut-in, and then production sequence. And the plots on the bottom just show you the data that we're gathering during each of these steps. So during the injection period, we are measuring that increasing pressure. This point here, we shut in and we measure that pressure fall off during the shut-in. And then once that pressure has stabilized, we're able to put the core on production. So we flow the core to a reduced back pressure. You can see here the gas rate declining over time here. And again, we use the flowing pressures and the rates to perform our rate transient analysis. So that's the procedure. Let's look at the actual example in a little bit more detail. For this proof of concept study, we used a Montney core plug sample from Western Canada. And some of the properties of it are shown here. So the porosity is about 5.7%. And the permeability as measured using a conventional pulse decay method is about 800 nanodarcies. So just shy of a microdarcy in permeability. So we chose this particular sample because in previous work by Ganizade et al., Ganizade works in our group, we've really thoroughly studied this sample and other samples from the Montney using a suite of petrophysical measurements, geochemical measurements, geomechanical measurements as well. And so we had a pretty good characterization of this sample already. And we knew that it had a relatively small total organic carbon content. We wanted that because we wanted to reduce some complications such as adsorption. We wanted to start with a pretty simple example before we started to complicate things. So again, we started with a very well characterized sample. Now, in terms of the experimental data, we followed the procedure that we showed you previously, and what we're showing on this plot is the post-pressure stabilization data. So after we injected the gas into the core, it stabilized at about 1450 psi. We then drop the pressure and we flow the gas out of the core plug. And you can see here the red is the gas rate data. And it drops very quickly over a period of just a few minutes against this flowing pressure of about 1250 psi. So we drop the pressure about 200 pounds to flow the gas out of the cell. So with this rate and pressure data, we can then follow our RTA procedure that we talked about earlier, our workflow, if you will. And so the first critical step, quantitative step in RTA is flow regime identification. So here again, we're plotting gas rate normalized pseudopressure. That's the light red line, or red markers, I should say. And the derivative of that is in dark red here. So again, we see this positive half slope corresponding to transient linear flow of gas along the core plug, followed by a positive unit slope corresponding to boundary flow. So again, going back to our conceptual model, transient linear flow early on, and then once this distance of investigation hits the end of the core plug, we enter the boundary flow period. So very consistent with theory, very consistent with the simulations that we ran quite a few years ago. We're able to reproduce that flow regime signature that we expected to see. So again, this is real experimental data, not simulated data. So the next step is, after having identified the flow regimes, we want to go through and analyze those flow regimes individually for properties of interest. So here what we're starting with is what we call traditional straight line analysis, SLA straight line analysis, and specifically the square root of time plot, gas rate normalized pseudo pressure versus square root of time. The actual data is again shown here in red, and you can see here we fit a line to this early linearized data. And from this plot, we're actually able to obtain two estimates of permeability and pore volume. The first method for estimating permeability is what we call the slope method, and it's based on, not surprisingly, the slope of the square root of time plot during the transient linear flow period. So extracting the slope of the line allows us to calculate A root K, the product of the cross-sectional area of the core plug and the square root of permeability. And since we actually know or can estimate quite accurately the area of the core plug simply by calipering the core plug, we can solve for permeability. So this is in contrast to the field case where it's very difficult for us to decouple permeability and fracture area. Well, fracture area. So here we actually know the fracture area, or cross-sectional area of the core plug in this case, and we can solve for permeability. The second estimate of permeability can be derived from the distance of investigation method, or DOI method. So here what we're doing is we're solving the distance, linear flow distance of investigation equation for permeability. So we first identify the end of linear flow, that's this vertical dashed line. That's obtained from our derivatives. If I go back to the previous slide, that's the start, or the end of linear flow is right around here. So we identify the end of linear flow from the derivative. That's the time at the end of linear flow, which is an input for the equation. That plus the length of the core plug and our porosity and gas properties allows us to solve for a second estimate of permeability. So we're getting two estimates of permeability, one from the slope method, one from the DOI method. Now, in terms of pore volume, we can obtain pore volume using Wattenberger's approach, again, combining the slope of the square root of time plot during transient linear flow, combined with the time at the end of linear flow, allows us to solve for pore volume, which of course allows us to derive porosity. So two estimates of permeability and a pore volume from the square root of time plot. Now, the other traditional straight line analysis method that we can apply is the flowing material balance plot. And remember, this is applicable to boundary flow. So a flowing material balance plot is the plot of gas pseudo pressure normalized rate versus normalized cumulative production. During boundary flow, this should again form a straight line, hence the term straight line analysis. And that will can be extrapolated to intercept the x-axis to derive the gas in place. And so once we have the gas in place, because we can measure the bulk volume of the core, we have some estimates of the gas saturation and the gas properties, we can solve this for porosity. So we get pore volume and porosity from the x-intercept of this plot. Now also, in addition to that, because we have an understanding of the geometry of the core plug, we can actually use the y-intercept to estimate permeability as well. So it's possible to get a permeability and pore volume estimate from the flowing material balance plot as well. So in this particular table, what I'm doing here is just summarizing the results of our traditional straight line analysis that we obtained for a proof of concept study. So this column here provides the information that we obtained from the slope method, which in this case is the permeability around 670 nanodarcies. The two columns next to it are our property estimates from the DOI method. And from the DOI method, we're able to get both permeability and pore volume. And the reason why there's two columns here is it depends on how you identify the end of linear flow. So there's a couple of different ways to do that. One's based on the square root of time plot, and the other is based on the use of the derivative. But you can see here reasonable consistency between permeability and pore volume estimates, depending on how we estimate that end of linear flow. And then lastly, from the flowing material balance plot, we're able to, again, get our permeability and pore volume, which is in reasonable agreement with the other methods. So it's important to us that this technique allows us to get multiple estimates of permeability and pore volume. That redundancy is something that you don't normally get from conventional core analysis. Usually you get one estimate of one property, and you're lucky to get more than one property from the test. So this redundancy is important, we believe, for consistency checking and making sure that you're deriving the same properties depending on the analysis technique. Now, what we just showed you was the results of traditional straight line analysis. In recent history, we've also been working on a new straight line analysis method based on the contacted gas in place approach. So what we do is we calculate contacted gas in place during transient flow and then ultimately boundary flow using Agrawal's method. So it uses the derivative of rate normalized pseudo pressure with respect to the natural log of material balance time. If you're interested in the details, it's in the book on RTA I wrote last year, but also there's a paper associated with this. And how it works is when you calculate the contacted gas in place, you see that during transient linear flow, you see a positive half slope. So that gas in place is growing during transient linear flow as that distance of investigation is propagating along the core plug. And then during boundary flow, you see a zero slope develop. So this plot is fairly easy to analyze for properties of interest. For gas in place, you simply extrapolate the straight line, horizontal straight line back to the y-axis to get your gas in place values. Notice the very small gas in place values here, very small fraction of a standard cubic foot. Remember, this is a core plug. So you get your gas in place, and just like we did with the flowing material balance plot, we can solve this equation for porosity. And then from the fit of the transient data, the transient linear flow data, we can extract A root K. So we have an intercept term derived from this plot that allows us to estimate A root K. And again, because we know A, we can solve for permeability. So this plot also allows us to get a permeability and a pore volume estimate from the core plug data. All right, so having walked through that analysis procedure, the next step for us was to compare the results to more traditional analysis. So we took the same core plug and performed a test, a pulse decay test, under similar conditions as with RTAPK, also using methane. So again, a pulse decay test is a very standard procedure in commercial labs for estimating permeability of tight rock. So we wanted to make that direct comparison. So here what we're showing you is the gas permeability for our proof of concept sample from the Montney. The red bar is the pulse decay derived permeability estimate. The blue bars represent RTAPK, and there's two sets because we did a repeat test on the sample to just double check the reproducibility. And the different colored bars correspond to the slope method and the DOI method, if you're wondering what all that's all about. You can see here that there's pretty good agreement between the RTAPK method and the pulse decay permeability, and there's also, of course, some repeatability between the measurements for RTAPK as well. So that's good. You know, we're seeing consistent results, but the real value of RTAPK is really the speed of the analysis. So after pressure stabilization, we were able to get both permeability estimates and pore volume from RTAPK within about 2 minutes. If we compare that to pulse decay, the results were obtained in about 30 minutes. Now, obviously, that's a fairly big difference in time, but where it really becomes valuable is when we're doing multiple tests on the same coreplex. So, for example, we typically measure permeability at different pore pressures. We'll talk about that here in just a minute, as well as different confining pressures and effective stresses. We'll quite often measure permeability on a core plug perhaps a half a dozen times at these different pressures. So now when you're talking about 2 minutes per test versus 30 minutes, that's a significant difference in time savings for the use of this RTAPK method versus pulse decay. So this initial proof of concept study, we were pretty happy with ourselves, and we published the results in a field paper in early 2019. The method was then featured in an Advances in Engineering article. This is an online magazine, so this group identifies what they think some novelties in engineering, and they selected our technique and featured it in the July of 2019 Advances in Engineering article. So it gave us some confidence that, hey, other people recognize this has value, and it allowed us to continue to explore the method and specifically try to expand the capability of the method. So as a result of that proof of concept study, we decided to apply for some federal funding through the Canadian federal government, the NSERC program, Natural Sciences and Engineering Research Council. And we obtained this federal funding to really start to expand the capabilities of RTAPK. And there's 4 different areas that we've been working on, which I'll just briefly touch on here. One is the investigation and extension of the dynamic range of the device. And what I mean by that is this idea that we can explore the lower permeability and higher permeability end members for the device. We can look at liquid phase permeability measurements. We can do 2-phase permeability measurements, i.e. effective permeability for 2-phase systems, gas and water, for example. And then very importantly, we can start to evaluate some of the complexities in RTA, such as how does reservoir complexity or anomalous diffusion affect flow regimes and rate transient analysis in general. So starting to solve some fundamental problems. So I just want to briefly touch on each of these. So starting with the extension of the dynamic range. So what we did here was we provided a new experimental setup. So we kind of redesigned the initial setup to allow us to analyze injection fall-off data. So that initial injection fall-off data that we obtain at the beginning of our test procedure. That allows us to explore lower permeability ranges and also gives us, again, more estimates of permeability and pore volume. And we also redesigned the device to perform some additional testing methods. So we'll be able to apply conventional core testing using the same device for direct comparison with RTAPK. So basically all we did was we added a pressure transducer in the upstream end, and we added a high pressure pump that allows us to measure rates and pressures during the injection fall-off period. So now we have the ability to analyze the injection fall-off right at the beginning of the testing period. So here we're just showing an example. This isn't the same sample we showed you earlier. But we measure the injection rates, the red open circles here. You can see that pressure increasing. And then we shut in and we observe a pressure fall off that we can then analyze using pressure transient analysis methods. So here we're just showing you the flow regime identification plot for that fall off period. So plot of pseudopressure difference and its derivative versus the delta pseudo time. And you can see here, again, a half slope developing during linear flow. And then we can also identify the end of linear flow as shown here. Having identified linear flow, we can apply our linear flow plot, which in this case is pseudopressure versus the square root of delta pseudo time. So from the slope of this plot, again, we're able to get permeability. And again, this is one of our efforts to expand the dynamic range of the device. We can also measure liquid permeability. The previous testing that we've been showing you has been with this device for gas testing, which is something that we developed back a few years ago. More recently, with a redesign of the experimental apparatus, we've been able to measure liquid permeability as well, such as water or undersaturated oil, etc. And just to show you some results of this, what we're showing here is a test with water, RTAPK test with water. We're using our modifier alternative straight line analysis method based on the contacted fluid in place. So here we're plotting water, contacted water in place versus material balance time on a log-log plot. We fit a straight line to the data to get our permeability, and then at late time we can extrapolate the horizontal line to get water in place. So you see here the data is a little bit noisier simply because it is more difficult to measure water flow rates than it is gas flow rates, but very important advancement because this expands our capability to look at things such as, permeability of flowback water. If you're interested in carbon capture and storage and saline aquifers, this is a method you can use to get permeability of those types of reservoirs as well. Now, moving on to the two-phase, this is kind of the really interesting stuff for us anyway. So being able to measure effective permeability to gas and relative permeability at different water saturations. So here, just to illustrate this methodology, we're using a Permian Basin sample this time, where we did RTAPK tests under different conditions of water saturation. So we started with an as-received sample with 22% water saturation. We dried the sample and then partially saturated it to saturations up to about 50% water, or just over 50%. And then back down to a saturation of 25%. Tested the sample at different stress levels during the loading cycle. We measured the water saturation before and after the flow tests. And then we determined the effective permeability using this new straight line analysis method, or the contacted fluid in place plot. Now we're going to show you the results of this in terms of a Klinkenberg plot, but I first have to explain what a Klinkenberg plot is. So for those of you that aren't familiar with this concept, it's possible when we measure permeability to gas that we could see gas slippage effects occurring that could affect our permeability to gas. And what we mean by this is that in a conventional system where the pores are big and pressure is high, for example, the gas doesn't interact significantly with the pore wall, and we can assume a no-slip condition where we see a parabolic flow velocity through the cross-section of the pore space. So no slip is what you would expect to see for liquids, for example, or gases at high pressure in large pores. So in conventional core testing, we typically don't worry about gas slippage effects. However, when we shrink the pore down to small sizes and at low gas pressures, you start to see significant interaction between the gas and the pore wall. And this can cause gas slippage along that pore wall interface. And that slippage adds to the flux, which causes us to get an overestimate of permeability compared to a liquid system because of this flux along the pore boundary. So a Klinkenberg plot is used to evaluate the degree of gas slippage that we're seeing in our system. And for that purpose, all we do is we plot gas permeability versus inverse mean pore pressure. So we're measuring the gas permeability at different pore pressures. And as that pore pressure decreases, which is to the right on this plot, we see an increase in gas permeability related to the gas slippage effects. So I had to explain that before I show you the data that we collected for our Permian Basin sample. So here what we're showing you is apparent permeability to gas versus reciprocal mean pressure for these different saturation levels that we talked about. So the green dots represent our dried sample, and we're seeing that classic Klinkenberg slip effect where the apparent permeability to gas is increasing. And then the other dots, the blue dots, represent water saturation of 22%, red is 25%, and black is 48%. You can see here that the slope is actually decreasing as we increase that water saturation. You can see this a little bit more clearly if we change the y-axis to a log scale. You can see that initially you see that increase in apparent permeability to gas, and then we actually see a reversal. And how we're rationalizing this is to look at the type of flow that's occurring in the core. So in the classic case where we have coexisting flow or funicular flow, that's where the two phases, the gas and water, are flowing through the same pore space. In that scenario, when water saturation is increasing, the pore size decreases and the gas slippage effect becomes more important. Now, in contrast, for segregated flow, where you have water occupying, say, the smaller pores and gas flowing through the more connected pores, the larger pores, then that can cause us to see this reversal in effective permeability trends. So we can actually start to look at the mechanisms of flow through the pore space just based on the character of this Klinkenberg plot. Now, of significant importance to us is this idea that we can also estimate relative permeability to gas at different water saturations. So here what we're showing you is a drainage relative permeability curve for gas. The different dots here correspond to different effective stresses, but you can see here in general we see this decrease in relative permeability to gas with an increasing saturation corresponding to a drainage relative permeability curve. So we're just starting to explore the use of this technique for estimating relative permeability as well. So significant advancement for us. Okay, the last topic I want to focus on, I'm running out of time here, is this idea that we can explore the impact of reservoir heterogeneity. So once again, we started with a Permian Basin sample. We measured the RTAPK effective permeability at different saturation levels. And unlike the previous case, we actually did some CT scanning on the core plug at different stages. So after the second installation, we actually CT scanned it so we could start to look at the microstructure and the fabric of the core sample. I'll explain why we're doing that here in just a minute. And again, we estimated the effective permeability to gas using our new straight line analysis method. Now, the previous cases that I showed you, pretty solidly seeing linear flow to boundary flow, half slope behavior followed by unit slope behavior. But for this particular sample, the as received sample at 37% water saturation, we didn't see a half slope early on. We saw this 3/4 slope followed by a unit slope. And the 3/4 slope obviously is somewhere between a half slope and a unit slope, and some people refer to this as sublinear flow. And so we weren't expecting this. And so we started to look into what may be causing this. And there's several possibilities. Of course, we are in a two-phase system. It's possible water is affecting the signature, sample heterogeneity, anomalous diffusion. But remember what I said earlier, we actually CT scanned the core plug and we could identify some fractures in the sample at different orientations. And so we believe at present that it's really the fracture heterogeneity that's causing this sublinear flow signature. And at present, what we're doing is we're actually doing some forward modeling using the CT scan derived fracture geometries to to see if we can reproduce this flow regime signature. So it gets back to what I was saying before, is this RTAPK method is allowing us to resolve or to address some very important fundamental problems facing us in RTA. So what is causing the sublinear flow signature? Some people believe it's anomalous diffusion. Some people think it's related to the fracture heterogeneity. Some people think it's multi-phase flow. This will allow us to really start to address some of these very fundamental issues that we are facing right now. So in conclusion, a new experimental procedure for determining matrix permeability is introduced to better reproduce the conditions under which wells produce in the field. The method produces flow regimes consistent with those observed from field data. The data can be analyzed using RTA methods developed for the analysis of well production data, and our proof of concept study using Montney core plug was performed, and several independent RTA permeability estimates are possible along with pore volume, and the permeability values are consistent with pulse decay values, but were obtained in a fraction of the time. In terms of the stuff that we're currently doing, we're trying to expand the dynamic range of the device. We can now measure liquid permeability with water, undersaturated oil, etc. We can measure effective and relative permeability to gas in two-phase systems. And we're currently using the technique to evaluate the impact of reservoir fracture complexity and possibly anomalous diffusion. And the method can be applied, and we're exploring this now, to different transitional energy concepts such as carbon capture and storage, geothermal, as well as hydrogen. And so we now have the ability to perform simultaneous injection and production, for example, in our current work. And it may be overstating it, but we believe that RTAPK could revolutionize laboratory-based permeability estimates. And with that, I'd like to thank the following: Ovintiv and Shell for sponsoring my chair, TOC. TOC sponsors the Canadian Government Funding Agency, Society of Petroleum Engineers, and Canadian Society of Petroleum Geologists, and of course Whitson, and specifically Matthias, for inviting us to present today.
Great, Chris. Thank you so much. We've gotten a lot of interesting questions here. We tried to answer some of them in the Q&A, and I've also gotten a few private ones here on the chat. Just for the entire audience, it's RTAPK. Can you just make sure what PK stands for everyone, so we're on the same page?
Sure. So RTA is rate transient analysis. P is really a reference to looking at the pressure dependence of permeability, and K is permeability.
Yeah, excellent. It's perfect. That just so everybody, because I got that question from a few folks. The few questions we have in terms of a lot of them goes on the core itself. Is there any limitations, or just the core has to be fractured or contained, etc.? And do you have any comments on how you get it from the field to the lab, and potential discrepancies or inconsistencies there? Because you always have this group of people, I would say, okay, when you take it out of the reservoir, it's not the rock that it was in the reservoir, type of thing, especially for these low rocks.
Yeah, so we have, with this techniques, we have the same issues that you have with conventional core plug testing, like pulse decay. So preservation of the core, if you're wanting to make sure you preserve the fluids, that's something that can be considered. Certainly with water, you want to make sure that you don't dry the cores out significantly before they're delivered to the laboratory. The idea of stress relaxation and the creation of microfractures, I mean, that's going to happen no matter what technique you use. And so what we try to do as a mitigating factor is we'll measure we'll do all the permeability tests at different confining stresses. And so that'll allow you to correct the permeability for stress. So if you want to reproduce a situation where you have a micro crack free sample, you can always use an extrapolation to get there. But it is an issue. It's an ongoing issue with core analysis. Is once we take those cores out of the ground, we're changing the conditions. We're introducing some cracks and things like that. And this technique doesn't solve that problem. But again, the conventional core testers try to mitigate that by doing the measurements at multiple stresses, so you can extrapolate to conditions at which you would expect those microcracks to be effectively closed.
Excellent. A lot of the other questions that come up here naturally with low perm rocks is like, what's the lower limit, whether or if you have a lower limit to liquid or to gas or just absolute perm. And that will actually be our last question just because of the time.
Because I ran over time. Yeah, I get it. So that's an excellent question. So that's one of the things we're continuing to explore right now with this device. But I can tell you the lowest that we've gone down to is effective permeabilities of about 15 nanodarcies, actually about 13 nanodarcies technically. And that was one of the effective permeability tests that we did here recently, where we were getting a value of about 13 nanodarcies. So the lower limit of a typical commercial pulse decay device is about 10 nanodarcies. So our lower end is about the same as a conventional pulse decay device for reference. On the upper end side, which is what we're still exploring, we did some coal sample testing recently, and the permeability levels were well over a microdarcy. So we think we can, and that's a microdarcy is about the range upper limit for a pulse decay device as well. So we think our dynamic range is at least as good as a pulse decay device, but we're continuing to explore that. But yeah, 10 nanodarcies is probably the practical lower limit. And you know, a few microdarcies on the upper end is kind of where we're at that side as well.
Excellent. Thanks, Chris. And I see there's a few questions that we weren't able to answer, but I'm sure we'll get more opportunities to answer them in the future. So with that, Chris.
Yeah, and if you like, sorry, Matthias, if you want to somehow forward them to my email, I can address them that way.
Yeah, 100%. That's exactly what I was planning to. Excellent. Thanks everyone. Thanks, Chris, again. Really enjoyable. I definitely learned a lot, and it was kind of the first time I looked at core stuff and I felt that I understand stuff. So that's always good. And with that, I'll wish everybody a good rest of their Wednesday, and we'll talk again soon.
Thanks for the opportunity. Take care.